We'll continue talking about electrochemistry today, last chapter of the year, and it fits into big idea 3. We're going to be looking at electron transfer, and with the type of electrochemistry we're doing today, we're going to be talking about voltaic, also known as galvanic cells, and these are electrochemical cells in which electric current is generated from a redox reaction that illustrates thermodynamic favorability. So with thermodynamic favorability, remember, delta G will be negative. There are many components that go into a voltaic cell, and I had asked you to watch both of these videos. The DeWitt video is very simplistic. It'll be a good place to start. We'll take a look at the second one because I want to point out a few key things. The components going into a voltaic cell include electrodes. You're going to have metal strips. You'll have an anode and a cathode. The anode is where oxidation occurs, loss of electrons. The cathode is where reduction occurs, gain of electrons. And we reviewed balancing equations last time, that is redox reactions, both in an acidic and a basic environment. So you should feel comfortable there. With electrode equilibrium, you'll establish equilibrium where the rates of the forward and reverse reactions are equal. And equilibrium is established at the surface of the electrode when it's immersed in a solution of its ions. And that statement right there may be a little confusing to you. For example, with the galvanic cell, and we can illustrate this out in more detail, but if you were looking at a half cell, let's say, for example, in this beaker, you have a strip of metal, and let's say it's copper. If it's in a solution of its ions, perhaps what you have here is some concentration, let's say 0.1 molar copper 2 sulfate, which is water soluble. So in solution here, you would have copper 2 ions and sulfate ions, and you're going to establish a half reaction depending on what it is. It depends on the other half cell. For example, let's say that copper 2 plus is being converted to copper, so you would be gaining 2 electrons, so this would be the reduction half reaction. And there are a few things I really want you to think about here, because I've designed several part 2-like questions, and I remember back in 2014 I designed a question and I asked different pieces of it, and it was really similar to the exam. And just these little pieces along the way will help you. So for example, if this is the reduction half reaction, as you go from left to right, copper 2 plus being converted to copper, what would you predict happens to the mass of copper as this reaction proceeds in the forward direction? It would increase because you are generating that solid. Okay, so just little things, and you'll see where it fits into the big picture as we go. But in regard to a voltaic cell, you're going to have an electrode, that's a metal strip, and it's immersed in a solution of its ions. So here what you've got is a situation where you have an aqueous solution, hence its ion here. Now, in some instances, you can't have that, and we'll get into that, but for right now, we'll keep it simple. So this would be a half cell. Now what you're going to do is you're going to put 2 half cells together. You are going to have what's known as a salt bridge. This is an upside down U-shaped tube. And so here you're going to have the other half cell, whatever that's going to be. We'll get into that in a sec. And here will be another electrode, and that should be immersed a little bit deeper here. You have a cotton plug here and here, and this is the salt bridge. And the salt bridge will contain ions that permit ion migration and prevent a buildup of charge. And we'll take a look at that in more detail in a little bit. But understanding the function of the salt bridge will be critical as well. You will have an aqueous solution in here, and it will be comprised typically of group 1 ions, and nitrate ions would be good too. So something like potassium nitrate would be a really good selection. So you would have potassium ion and nitrate ion. So potassium nitrate, we know, generates potassium ion and nitrate ion. And we'll talk about which way those ions are moving in just a minute. But you really want something from group 1, and nitrate ions are a really good choice. Sometimes potassium chloride is used, but you have to be careful if there's silver ion present, because you'll generate a precipitate that you don't want. What you will also have in a voltaic cell is a voltmeter, and this is something that will measure the voltage, and we will be constructing little batteries after break where you'll be using voltmeters and different metal strips. Our salt bridges will be very simplistic. It's just filter paper dipped in potassium nitrate, but you can use these U-shaped glass tubes. So with a voltmeter, it's going to measure the difference in electrical potential between 2 points in an electrical circuit. And shown here, you've got galvanic, also known as voltaic cells. Here's the anode. So what you're going to find at the anode is that oxidation occurs, and the cute little way you remember that is anox and red cat. So at the anode, oxidation occurs, and we know oxidation is a loss of 1 or more electrons. Reduction occurs at the cathode, and we know with reduction we have a gain of 1 or more electrons. So anox red cat, and that will help you. So in the example I scribbled out for you here, we had reduction. So reduction would be at the cathode or the anode? Cathode. So this would be considered the cathode as the electrode here, because reduction's occurring. And in your notes here as well, you can see here's a half cell, here's a half cell, here's the cadmium electrode, here's a solution of cadmium 2 ions. So let's say, for example, you had something like cadmium 2 nitrate, whatever it might be, just something soluble. Here's a silver electrode. So this would be in a solution maybe of silver nitrate or some silver ion containing solution that's water soluble, that is. Make sure you don't use things like silver chloride, that forms precipitate. Here's the salt bridge. We'll talk about ion migration here because that'll be important. You're connecting the circuit together, and here you don't have a voltmeter, but you're just detecting whether you're generating flow such that the light bulb illuminates. So the electrons move through this wire here. This is the salt bridge, which permits migration of ions. And if you look at that one, for example, what they're showing you there, and we can show it off the one I initially made for you, is they're showing this equation and this half reaction. So which one is oxidation? This one? And oxidation occurs at the cathode or the anode? So this must be reduction, and reduction occurs at the cathode. Here you're generating cadmium 2 ion. Here you're generating silver with a loss of positive charge, if you will. So if you were considering your salt bridge, and in your salt bridge you have potassium nitrate, if you're generating positive charge here, would you want more positive charge to go toward it or negative charge? You don't want a buildup of charge. So opposites attract. So the nitrate ion is what would be moving toward this cell or half cell, preventing buildup of charge, where here the positive charge, if you will, is disappearing as silver gets made. So here you want positive charge moving in this half cell or into this half cell. Does that make sense? Okay. So in this half cell here, and again that would be in there, your electrode would be cadmium, and in this half cell your electrode would be silver. And what would happen to the mass of the silver electrode? It would increase as more silver gets generated. And what would happen to the mass of the cadmium electrode? It would decrease as this undergoes oxidation. Okay? Couple things to think about as we go, and you'll see it in the video a little more clearly. Now, if they just give you 2 electrodes, there is a way to determine what gets oxidized and what gets reduced, and we'll take a look at that. There are some very common voltaic or galvanic cells for batteries. Dry cells, for example, typically involve zinc. Alkaline batteries, which we use all the time, also involve zinc, but a different reaction. There are nickel-cadmium batteries. What's in our cell phones? Lithium? Here's a lead-acid battery. That would be more of what you find in cars, correct? I don't know. We tend to use a lot of rechargeable batteries now. I do. We don't. And they have like these special batteries that are supposed to be so wonderful for Wii and all your little video game consoles, but I don't think they're so great.
Most of the tech we use these days, like rechargeable, is lithium-ion, like some form.
Yeah. But what about? Are you sure with the cell phones?
Yeah.
Okay. That that's probably this one. This is one type of lithium battery, but again, this is from your textbook, which is a little bit older. In any event, let's take a look at the following reaction here. We have zinc generating zinc 2+, so that's oxidation. Would that occur at the anode or the cathode? Anode. Copper 2+ generating copper, so that would be reduction at the cathode, red cat. And the DeWitt battery breaks down all the pieces, if you will, so you can take a look at that video. This one's pretty simplistic. We'll take a look at this one, but it's a good one. I like it.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution.
Now, if the anode is a zinc bar, let's make sure you have the pieces. This is where I think things just sometimes get murky. If the anode is zinc and the anode or the cathode is a strip of metal, so it's going to be a metal, a solid, no charge, no subscript. At the anode, you have oxidation or reduction. Okay, so are you going this way or this way? Okay. First piece of the puzzle.
And the cathode is a copper bar placed into a copper 2 sulfate solution.
All right, so if that's zinc, the cathode is copper, so that's going to be reduction. And what will the equation there be? Copper 2 ion plus 2 electrons yields copper. So which electrode is going to increase in mass? The copper one, because copper is being generated due to the reduction reaction. Clear so far?
The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate.
Okay, let's think about the salt bridge, and I know I'm going back and forth a lot, but I'm hoping the pieces will fit together better. If you have sodium chloride in that salt bridge, you have sodium ion and chloride ion. Where would you want the chloride ion to go? Into this one to prevent positive charge buildup. So the chloride ion, just leave it on my desk right there, thank you. The chloride ion needs to go in this direction to prevent buildup of positive charge. Zinc chloride is water soluble. Whatever you throw or let migrate in this direction better not cause a precipitate. In contrast, you're pulling positive charge out here, so you're getting less positive, if you will. So in this direction, you're going to send the sodium ion. The salt bridge permits ion migration. These ions are migrating, and it prevents buildup of charge. For example, you don't want a buildup of positive charge here. Function of the salt bridge. It's been asked. They've asked which direction the ions flow.
Attaching a cell shows that electrons flow from zinc to copper.
Why do electrons flow from zinc to copper?
They're looking to
which substance gets oxidized? The zinc. So it loses electrons. Remember I said initially how our electrons transferred in previous problems way back from chapter 4, and we talked about it also last time. It's always transferred from the substance that gets oxidized because it loses to the substance that gains. Careful.
Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom.
Note the mass of zinc decreasing.
The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions.
And that's an important point that may not be visible the way we've drawn it here. It's easy to figure out why the negative ion migrates here to prevent this buildup of charge. Here you're seeing the positive charge disappearing, if you will, so we're throwing positive in. But also in this beaker you had copper 2 sulfate, so you have copper 2 ion and you have sulfate ion. You can see the loss of 2+ charge here when you generate copper, and you can see that the mass of the copper electrode would increase. You could see that visibly. You could also mass the electrode before and after the reaction. But you also have now a negative charge buildup, if you will. Sulfate is, of course, 2-, and you will then have the sodium ions migrating in to prevent the buildup of sulfate ion negative charge.
The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
And there you're just summing the two equations together. Drop down, those cancel, drop down, drop down, drop down. And like I said, I like that little video. I know I broke it up a lot, but hopefully the little pieces come together. And then the DeWitt video really goes over the different pieces of the voltaic cell. So that's something you'll want to take a look at, and you already should have watched it as recommended. We mentioned the anode. This is the source of electrons. It is the negative electrode. You don't need to know that. Electrons flow through the metal wires and the voltmeter, carrying current to the copper electrode, in this case, reducing it. The cathode is where the reduction occurs, as we mentioned. Couple key points I want to make clear. Cations and anions, not electrons, carry electric charge. You're going to see here as we calculate voltage that 1 volt is equal to the energy in joules per the charge, which is in coulombs, and we'll get into coulombs in more detail. The cell potential, abbreviated E cell, is the driving force that propels the electrons from the anode where oxidation occurs to the cathode where reduction occurs. You can also generate these cell diagrams and use an abbreviation system to represent what's going on. Typically we put the anode on the left, so that's where oxidation is going to occur. The cathode on the right. Don't assume it though on a part 2 question. It's probably not going to be that straightforward. A single vertical line represents boundaries between different phases, such as the electrode and the solution. So the solution could be something like zinc sulfate. The double vertical line represents the salt bridge. You also can use an inert electrode, and you'll find this to be the case if you have a situation where you're reducing or oxidizing and you're not generating or consuming a solid. So for example, iron 2 plus can lose an electron to form ion 3 plus. Here you don't want an iron electrode because you don't want iron generated or consumed. So use an inert electrode such as platinum. You also see that, for example, if you have a gas such as chlorine gas, you would want an inert electrode, and we can point that out. You had a question.
Like when you were talking about the different types of batteries, would something like a mercury battery work?
What would you use a mercury battery for?
Like for some, like non-rechargeable?
It's a mercury battery?
Yeah.
Are you sure? I really didn't think that they used mercury batteries all that much anymore because mercury has been shown to be a carcinogen. So I don't, what kind of batteries are mercury-based batteries?
I was just wondering, like.
Yeah, that's not something that, you know, and it's funny that you mentioned this because I even asked the dental hygienist yesterday because I said to her, you know, we were teaching about solutions and I know amalgam is mercury dissolved in silver. And I said, they don't even use silver fillings anymore, but yet some of us still have them, so they have mercury in it. And she said, well, once everything solidifies, the mercury is not dangerous to you. It was more dangerous to the people who were putting the fillings in. And in regard to the battery itself, the battery might be fine unless it broke open for some reason or leaked. And that would potentially have deleterious or harmful effects. So do a little Googling, but I don't think they use mercury batteries very much anymore.
I know that, I don't know if they still do this, but the watch batteries, you know those small round batteries, they had tiny amounts of mercury inside of them, and that's what they used them for. I don't know if it was...
What do you mean a watch battery? Like, do you mean like a stopwatch battery?
Like the little...
No, I know what you mean, because that's what's in the pH meters, that's what's in the voltmeter, those little button batteries. They have mercury in them?
Yeah, they have small ones.
I think torque is leaking.
No, it's not a driving thing, but they have small amounts of mercury in them.
And that's interesting, because those things leak all the time.
I don't know if it's liquid mercury, though.
Well, what else could it possibly be? Mercury is a liquid.
I mean, it could be solidified.
So, but, well, the question is what's leaking out of them,
So my family's in like.
which I think is acid. Go ahead, what?
My family's in like RC stuff and helis, and I did a walk through my house to try to collect like batteries that were puffed up. I counted 12 lithium-ion batteries puffed up that I had to take to like the solid waste authority like last week. Like nothing. Family's in that. Like, is lithium dangerous in that sense? Not really. Yeah, I know it's reactive. That's why I'm taking a lot of bad batteries.
I don't know. Do some research. Let us know. What do you got?
It says mercuric oxide batteries are still produced for the military and medical equipment.
What kind of medical equipment? That looks like a great project after the exam. We'll look into that.
Or we could just like blow up some batteries.
Yeah, sure. I don't think so. Alrighty. The other thing I really want to show you today is how to calculate standard cell potential, and it looks really hard, and I promise it's very, very easy. This whole chapter actually is pretty straightforward. It's nothing like what you've just survived. The only thing that's challenging is that it's all new material because it's not material that you delved into in any regard in honors, so that'll make it a little more challenging. We're going to take a look at standard electrode potentials. We've got to have a 0 point or a reference point, and that's going to be a standard hydrogen electrode. So for example, 2 protons reacting with 2 electrons to generate hydrogen gas, you'd need a platinum electrode there because this is a gas. And here, your standard electrode potential would be 0 volts. Now they don't provide you with a table such as this one anymore, And no, you don't have to memorize it. It's actually just a little bit easier for you. I'm just going to refer to it because you'll need it to do your homework. But if you had any type of multiple choice question or a part 2, they would give you the values or give you a very tiny table, so you don't have to spend time looking through this. But in any event, the reference point is for hydrogen. So you have 2 protons reacting with 2 electrons to generate hydrogen gas. And here your electrochem potential would be 0. So that's the reference point. Anything above it is more likely to be reduced than proton. So sulfur, tin 4, copper 2 ion, etc. These are more likely to be reduced than proton. Anything below it is more likely to undergo oxidation. So here you're looking on the right side. Lead is more likely to be oxidized than hydrogen gas, tin, nickel, cobalt, cadmium, etc. And this actually is what explains your activity series for metals, because if you go way down low here, you'll see lithium at the bottom here, and lithium is the most active metal in regard to single replacement reactions. It's most likely to be oxidized with a negative 3.05 voltage. The substance most likely to be reduced would be fluorine with a 2.87 voltage. So that's a standard reduction potential chart. Everything is listed as a reduction, but again, anything below proton at 0, these substances are more likely to be oxidized. When we say standard, concentration would be 1 molar and gases would be at 1 atmosphere of pressure. You can establish standard electrode potentials for other half reactions by constructing voltaic cells where one of the half cells would be the standard hydrogen electrode. We're going to be doing this in the lab, but our standard electrode is going to be zinc because we're not going to play with flammable hydrogen gas. Standard cell potential, and this is E, the naught sign for standard, again 1 molar concentration, 1 atmosphere of pressure for the cell. So now you've got 2 half cells together, is calculated cathode minus anode. If you do cathode minus anode, you never have to change the sign of anything. You just look at those values and subtract them. Cathode minus anode. Your review books may show you differently. Do it however you want as long as you do it correctly. A positive value for E cell indicates that the ions are more easily reduced. A negative value indicates that the ions are less easily reduced than proton, and that's what I was saying to you before. Here's your baseline. These substances are more likely to be reduced than proton. These substances are less likely to be reduced. These substances more likely to be oxidized. When you go to calculate it, it's really pretty simple. It's going to look a little bit like Hess's law, but it's not going to be applied the same way. Be careful here. It says calculate the standard cell potential for the following voltaic cell. You've got zinc going to zinc 2+, so that clearly is oxidation at the anode. This value would most likely be given. Copper 2+ to copper, that's the reduction at the cathode. All you have to do to calculate the E cell under standard conditions, so calculating standard cell potential, is cathode minus anode. So this and this may be given. You figure out oxidation, reduction, anode and cathode respectively, and you do the cathode minus the anode, and here's your E cell. Let's take a look at this one. That's all that's given. So we're going to work a couple problems. You'll see it's pretty straightforward. So I've given you 2 reduction potentials. So that's like in a table that would be provided. I've given you a bare bone equation. From this equation, I can see that silver ion is going to silver. So we're gaining an electron. Is that reduction or oxidation? That's going to be reduction, gain. Leo the lion says grrr. Reduction occurs at the cathode. The other reaction is nickel going to nickel 2 plus. That's a loss of 2 electrons. That's oxidation at the anode. I'm not changing any signs even though these equations are flipped around. I've got in volts, that's a V. I've got 0.80. And for the nickel, I know I flipped the equation, but I'm not changing the sign. If you want to do cathode minus anode, don't change any signs. To get the standard cell potential, that's E cell naught, I do cathode minus anode, and this sometimes is without a calculator. Please don't make a silly boo-boo. The other thing I want to mention, you'll see more of this. If you have a voltaic cell, and you do here because that's all that you've learned about so far, E cell must be positive. Now in this problem, very simple, we just did cathode minus anode to get E cell. You can be given this E cell under standard conditions, and you can be given one of these and have to determine the other piece. And that's what I'm showing you here. And we're going to be doing a ton of these as we go. I've only given you a few examples here, but you'll get it with ease. It says determine E for the reduction. So you want to determine the cell potential for the half reaction under standard conditions. This is the half reaction you're trying to figure out. You're given the cell voltage for the cell in general. That's right here. That's what we calculated previously as cathode minus anode. Here you're given it. And you're given the reduction potential for cobalt-2 ion to cobalt. So how are we going to approach this one? This is what's given. You've got and it says 1 molar or aqueous. Then you've got the double bar, that's where the salt bridge would be. Here's C4 plus, and again 1 molar, so that's aqueous. Ce3 plus, again 1 molar, so that's aqueous, and this is going to require a platinum electrode because you don't want to generate that solid. E cell overall is 1.887 volts, and the only other piece of information that is provided to you as follows. So how do we do it? Now be careful, because you have this. you know the way this equation was written, that this is the reduction or the oxidation. Gain, reduction at the cathode. So therefore, the other equation here, and you can tell the way it was written here, that this is the oxidation at the anode, correct? And when we want to calculate E cell, it's cathode minus anode. So the E cell that was provided to us was 1.887 volts. The cathode is what we're looking for, minus the anode. So yes, the equation's flipped around, but don't change the sign if you want to do cathode minus anode. And so you would have 1.887 minus, because you have a minus a negative, 0.28. And so my cathode then for this missing equation here is equal to 1.61 volts. And you can go back and check your work, cathode minus anode, which will give you E cell overall. Yep.
Couldn't we just leave the cobalt one as the cathode and then solve for the anode? And then use something to find the... Never mind, wait. No?
So you can either solve for E cell or you can solve for a piece, and just be very meticulous in your setup and you'll be successful there. Cathode minus anode, provided that you don't change any signs. And you'll see that the reason you can do this is electrode potentials and cell voltages are intensive properties, so they don't depend on the total amount specified. So even here, and that's an important point to make, when you go to balance this equation, you have 2 electrons here, so you're really going to have this, but you don't double down or half or whatever they give you, you use. You don't double it, and we'll make that point more clear. You would have seen it here as well. We never went back and balanced this equation, but here, you know you need 2 electrons transferred, and even though you're multiplying by 2 here, you do not change this. Don't multiply it by anything. Don't change its sign. Keep it the way it is, cathode minus anode. And then when you go to balance that equation, you're balanced for charge and atom here. And we'll open up with a few more of these next time. We'll get into the link between electrode potential, spontaneous or thermodynamically favorable reactions, and equilibrium. We're going to be linking delta G, thermodynamic favorability determination, to E cell. Very, very simple. Don't foresee any difficulty with it. What you want to make sure you have today, do you know the parts of a galvanic cell? Can you identify what's getting reduced, what's getting oxidized, what will increase in mass, what will decrease in mass? Do you know the function of a salt bridge? If you didn't watch those videos, go back and watch them. We'll pick up next time with the thermodynamic favorability link.